This is networking. This is Nate Lawson and Taylor Nelson talking about exploiting remote timing attacks.
All right, let's make sure it's working. Okay, great. Yeah, as I said, we're going to talk about exploiting remote timing attacks in widespread systems. So who we are, basically Taylor and I work together at Root Labs, and we do security design and analysis for other companies. Our focus is smart cards, embedded systems, set-top boxes, game consoles, pretty much everything except most software systems. We do some software protection, DRM, and reverse engineering, so we like doing that kind of stuff. As well, crypto and protocols tend to be the glue that hold all these markets together. So I'm founder of Root Labs, and before this I was at Cryptography Research, where we also did a lot of work in side channel attacks. And while I was there, I co-designed the Blu-ray disc content protection layer. And Taylor is a Cal Poly student, which is where I also graduated from. And while at school, he works in the RFID tech lab there. But right now, he's been helping out at Root Labs. And he did a lot of the research for this talk. After spending so much time staring at picoseconds and nanoseconds and millions of samples, this quote seemed kind of appropriate. So what's a side channel, and what's a side channel attack? Basically, a side channel attack is actually where you can figure out a secret a device has, either a cryptographic key, a password, an implementation-specific secret, and basically observe the device handling that secret and figure out what that secret is. It usually requires close access, especially the first timing attacks were involving like smart cards, embedded devices where you had close access to it. But that's been improving. We're going to talk about it more in remote attacks. Also, it's usually non-invasive. For things like glitching or some of the work that Chris Tarnowski is doing after this session, that's invasive, where you take chips apart and you use chemicals and things like that. And side channel attacks aren't invasive. There's many kinds of phenomena that leak information. For instance, the power consumed by a chip or system, the electromagnetic emissions, heat, and even sound. For instance, one of the findings that a couple research did a few years ago was that the capacitors that are part of your motherboard actually leak a little bit of sound timing or sound information based on the idle states the CPU is in. So you can actually see different rounds of a cryptographic operation based on the sound. Well, timing's different. That's what we're going to talk about today. Timing attacks are potentially exploitable from remote. Sometimes aren't, sometimes are. And usually, a timing side channel is different from these other side channels. These other side channels usually give you intermediate information about a cipher, for instance. So you might be able to observe a round key being used multiple times in different rounds of like AES or DES. Whereas with timing attacks, you usually only get the aggregate. So you get the start time and the end time, but nothing in between. Now, that's not actually true for cache timing and branch prediction attacks. We'll mention those briefly later.
All right. So how exactly do you perform a timing attack? Well, you first have to find a function that handles secret data whose timing varies based on that secret data. So after that, you're going to want to set up a client to query this server, device, whatever. And so you query it, send out the response, measure the response time and the reply time back. Then you vary the guesses of your secret. So if you were guessing a password, you might do like A, then B, then C, then D, and so on. You want to do this a lot of times. So you got to sample a lot per guess. Oh, my bad. Sorry, guys. New here. All right. Next, you perform statistical analysis on these sampled data. So based on the target behavior of the given device or software, whatever you're targeting, you sort of make predictions based on when the guess is partially correct. Then you repeat until the entire secret is known. So this is a simple timing attack. You've got client, target. So you send out a request like 1273.
Take the timestamp.
Yeah. Response time is 1684, whatever that is. And the delta is 411.
So this is just a simple timing attack, and you can do more sophisticated things. The main thing that people need to get from this, the main intuitive leap, is that you only need to measure the difference of response times, not the actual response time itself. So, for instance, a lot of people will say, well, when I'm pinging my server, the response time, the round trip time is on the order of milliseconds, but you're claiming to be able to attack and find differences as small as microseconds. How can that be? And the reason is because you're measuring the difference in the behavior between sets of samples, not the absolute value of what those samples, what the server did. For example, you can look at two sample subsets and say, hey, the difference of means in these two sets is 10 microseconds, but you can't really know without analyzing the server in more detail whether that was actually a 1 nanosecond difference in compute time or a 1 microsecond difference. It could be anything in between. All you know is that there is a difference and you found something significant. So a little background, local timing attacks first, since those are where timing attacks first showed up. Back in 1995, Kocher published the main paper on cryptographic timing attacks, talking about how to find the bits of an RSA private exponent by timing the entire operation. And the way he did that was he realized that it takes a different amount of time to square a value in modern processors rather than multiply values. So RSA involves both square and multiplies typically in some implementations. And a square is just shifting, and a multiply is actually a heavier weight operation. So he was able to use that to figure out the bits of the private key. That moved on most recently in 2006. Dan Bernstein of QMail fame did some simple cache timing attacks against AES. And there was a parallel result at the same time by Colin Percival about attacking RSA based on the cache behavior. And he actually did an attack called prime plus probe, where you basically have two threads running at the same time, one doing the cryptographic operation and the other one timing accesses to its own memory. And from that, deciding which cache lines were hit by the AES S-box operations. A similar attack, but optimization of that one, was the attack by Osvik, where they basically did what's called evict plus time to measure differences of the AES cache behavior. And evict plus time is a little more sophisticated. What you do is you basically evict cache lines from the CPU in a predetermined array, and then run the cryptographic operation in its entirety. And then after it's complete, you go back and remeasure access to the same cache lines and see how long it takes to access them. If it takes a long time, then obviously no one touched that page in the meanwhile. If it goes really quickly, then you know that the process you're trying to analyze or some other competing process happened to touch the same cache lines. So that's a slightly more powerful attack. I kind of think of it as like taking some photographic paper and putting an object in front of it and then shining a light on that object. You'll see a shadow created on the photographic paper, and you're sort of seeing a shadow in the cache of the operations that happened while you were waiting. And then finally, the most powerful attack of this set, using the branch target buffer. So modern CPUs have branch prediction buffers, and they use this to optimize loops and other things like that. And if you're running a series of jumps and the addresses of these jumps happen to collide in the branch target buffer with the process you're attacking, then you can actually see when the process takes or doesn't take equivalent branches. Now moving from local timing attacks to remote timing attacks. So there's two really important papers in this series. The first one was Remote Timing Attacks Are Practical. This is the Brumley and Bonet attack on SSL in 2003. They actually were able to find the OpenSSL private key by measuring basically the time it took for OpenSSL to do a computation on that private key. And this was measuring a difference that was actually relatively large. It was about 16 microseconds on a 1.8 gigahertz CPU. That's a large difference. Most people think that's kind of small. And this attack was improved by a name I can't pronounce. He basically did an improvement by correlating the Montgomery table initialization in addition to measuring the timing of the exponentiation operation itself. And he's been making continual improvements in characterizing the differences of RSA operations. In this paper, they actually attacked an OpenSSL implementation over the LAN, and then they actually improved that and attacked the same OpenSSL implementation over multiple hops on their campus area network. So that was pretty impressive. And then going beyond that, the most recent paper in this series was Opportunities and Limits of Remote Timing Attacks, where Crosby and Dan Wallach, Rice University researchers, basically went out and said, let's figure out on the internet actually how exploitable timing attacks are. Let's take a bunch of different hosts and time the operations between them. We'll control every variable we can to see what's the optimal case for an attacker. And this was the first paper that actually said empirically what kinds of hosts are most vulnerable, what configurations are most vulnerable, and things like that. And a very important paper that we're going to talk about a little bit more. Basically, in this paper, what they did was they created a server that would do a delay loop. And the client could request a delay of a nanosecond or milliseconds or whatever. And the server would respond in the specified time frame. So it would also report how much time it actually took for this request to be processed. So you could actually correlate the measured response time to the server's actual calculation time. And they measured this on a bunch of different vantage points, like LAN, as well as Planet Lab, which is an overlay network. And so Planet Lab has thousands of hosts on it where people voluntarily collaborate on networking research. And so they use Planet Lab hosts to find out, what kinds of hosts are possibly vulnerable to this and how vulnerable are they. So the first interesting result was that response times aren't Gaussian. I mean, anyone here had basic statistics? Gaussian, your hump and your two tails on the side. So if you look at this distribution here from their paper, it's not Gaussian. You have basically a single peak and then a long tail off to the right. And so traditional statistical methods don't work as well when your samples aren't distributed according to the Gaussian. The vertical axis, sorry, this is a histogram. So the histogram is a count of the number of samples for each of the response times there. So the horizontal axis is latency in milliseconds. So about 15,000 samples were at that peak there. And you basically bucket based on the results. So because it's not Gaussian, the mean and median, which is typically how you do traditional statistical tests, aren't good measures. Another thing they found was that, people think, well, just take the minimum response time, right? So take a bunch of measurements, take the smallest one, and that's your estimator. This was actually shown to be not the best estimator by them as well. If you look at these different percentiles, these are basically the number of responses that came in, the response time in microseconds for the requested server processing time in microseconds. So as you can see at the far left for the 0th percentile, which is basically the minimum of the distribution, there's more noise there. But once you get to the higher percentiles, there's less noise at the lower response values. So basically, they found a lot of interesting things about network behavior. They found that actually network distance is not a good predictor of noise. So people think, well, the more hops away, the more noise you'll have. And that's partially true. If you have bad intermediate hosts in between, bad routers or whatever, you do get more jitter the farther away you are. But if you have a really awesome network, say in Sweden, it doesn't matter that it's around the world, because remember, you're measuring differences in processing time and response time, not the absolute value of these things. So even if you're far away, if you have a good network, it may be better to attack that host. A traffic shaper and other mid-layer boxes do tend to add a lot of jitter. And competing loads on the same host. So what they did was they took that same host that they're measuring and ran Apache on it and basically pounded it to 100% CPU load and found that it added about 5% unfiltered jitter to the end results versus an unloaded server. So these are some myths that people tend to have about the exploitability of timing attacks that just don't turn out to be true. In their final results, they had a really impressive number. Basically, they found that they could distinguish reliably differences of 200 nanoseconds over the LAN and 30 microseconds over the internet. And these numbers may be below what most people would think are observable. They used only 1,000 samples. When we read this paper, we thought, first of all, how could this improve with more samples? Next, what about new vantage points, such as cloud computing? If you're on EC2 and you can have servers sort of near neighbors that you don't own, what does that give, advantages that give an attacker? And then also, for common languages, what kinds of deltas are we looking at, compared to C and Java and other things like that? So